Okay, so today we have Haydar Göral from İzmir. This is his second talk in this seminar series, and today he's going to talk about counting arithmetic progressions modulo P.
Thank you very much for introducing me. Yes, this is my second time. Last time I think I talked on Lemmer's problem. So this time it will be more into number theory, counting arithmetic progressions modulo P, or finite field with P many elements. So what is an arithmetic progression? It's a sequence, either finite or infinite, does not matter, but the consecutive terms have the same difference always. So it starts with some number a, then jumps is always the same number, a plus d, a plus 2d. And if the common difference is not zero, then this arithmetic progression is called non-trivial. So this is the arithmetic progressions that we care, because if you have a non-empty set, you can always find trivial arithmetic progressions, the constant sequence, so which is not very interesting. For example, some infinite arithmetic progressions, even integers or odd integers. And also this sequence, for example, 5, 11, 17, 23, 29. It's a 5-term arithmetic progression in primes. So the whole story began with the term of Dirichlet. So it's almost 200 years ago, and sometimes called the birth of analytic number theory. So the idea is to subtract primes from arithmetic progression. So whenever you have a reasonable arithmetic progression, means A and B, they are coprime integers. And if you consider the arithmetic progression, A plus B, A plus 2B, so those are the numbers which are congruent to A modulo P, then you can find infinitely many primes in this arithmetic progression. And actually, if you consider those primes in this arithmetic progressions, and if you consider the reciprocal sum of those primes, this sum actually divergent. It's a divergent sum. For example, as an example, 3, you always said 1,000. 1,003, 2,003. Of course, they cannot be prime all the time, but you can find infinitely many primes in this sequence. And the proof is based on some multiplicative number theory called L functions. And if you use the L functions and non-vanishing of them, you can prove this theorem. So this is the idea. This time, you are looking at an infinite arithmetic progression, then you extract some special numbers from this. Then the other question is, if you are given some sequence, can you find arithmetic progressions from this sequence? The reverse question. So the leading question of the talk is, which subsets of positive integers contain arbitrary long arithmetic progressions? Arbitrary long means it contains a 3-term arithmetic progression, 4-term arithmetic progression, or it contains k-term arithmetic progression for every k, but it doesn't mean that it actually contains an infinite arithmetic progressions. So they are really different things. So if it contains an infinite arithmetic progression, of course, it contains arbitrary long arithmetic progressions, but the other way around is actually wrong. And the first famous theorem in this domain is the theorem of van der Waerden, and it basically states that you fix R and K. R is the number of colors, and K is the length of the arithmetic progression. And if you color the positive integers using R many colors, then actually you can find monochromatic k-term arithmetic progression. Or in other words, if you consider the positive integers and if you divide this set into finitely many classes, then in one class you can find arbitrary long non-trivial arithmetic progressions. And this theorem actually dates back to 1927, almost 100 years ago. And the proof uses combinatorics, but you can also, prove this theorem using some topological dynamics. Okay, so I already mentioned this. containing arbitrarily long arithmetic progressions and containing an infinite arithmetic progression, they are not the same. And the basic example is you can consider this sequence. So you use just two colors, blue and red. So the color of one is blue. Then you use 2 times reds, then 3 times blues, then 4 times reds, then 5 times blues, and so on and so forth. You continue like this. Then you said you can realize that both colors actually contain arbitrary arithmetic progressions, because at some point you can find k consecutive numbers. They are all reds or blues, but actually any color here, blue or red, I mean, they cannot contain an infinite arithmetic progression, because if one of them contains an infinite arithmetic progression, then there should be a jump, right? D. So you start with some number A, then you always add D. But at some point, say that, for example, blue ones contain an infinite arithmetic progression, but then at some points you can find too many reds, and if you add D, then eventually you fall into this gap, and your number will be a red number. So they are both dense, big classes. They contain arbitrary long arithmetic progressions, but none of them actually contains an infinite arithmetic progression. And in this topic, the notion of density is very important. And whenever you have a subset of positive integers, call it A, the upper density is defined by this limit. Lim sup when n goes to infinity, you intersect A with the first n numbers, you take the cardinality and you divide by n, you consider the lim sup, because actually the limit sometimes may not exist, but the lim sup always exists. So, and this is denoted by d upper A. So this is the upper density. Of course, similarly, you can define the lower density or natural density. But for the purpose of this talk, the upper density is enough. So basically, it tells you that if you intersect A with the first n numbers, this means you are considering the numbers from A which fall into the first n numbers. And if you divide by n, this is kind of a probability, right? This means that whenever you choose a number from the first n numbers, this is the probability, a number that you get from A, right? This is the probability. And actually, if you take the limit, this tells that, the probability of A is big enough or not. In a sense, of course, this is not a probability. It doesn't obey the rules of the probability, but you can think like this, okay? And for example, the basic example, always, the arithmetic progression. If you consider the infinite arithmetic progression, a plus b to the n is the natural numbers, then of course, as expected, the density, the upper density is 1 over b, because you always add b, right? Out of every b number, you choose 1. And the second example, if you consider this set, so the numbers is, you start with 10 to the n, then you add n numbers. But for every 10 to the n, you are adding n many numbers. So this means your increase is linear, but your jumps are exponential. So you can observe that actually the density of A is 0. It's like the logarithmic density, more or less. But as you see, it contains arbitrary long arithmetic progressions because you forced it, right? Because you see, for example, whenever you have n between 10 to the n and 10 to the n plus n, you can find a long arithmetic progression in this set. But actually, this set is very small. Its upper density is 0. But if you consider its complement, this time your upper density is 1. The complement also contains arbitrary arithmetic progressions. But since in A you can find arbitrarily long consecutive integers, then similarly, the complement cannot contain an infinite arithmetic progression. So these are the basic examples. From the algebraic point of view, you can consider the squares. So 1, 4, 9, okay? Then the density, of course, is 0 because up to x, there are more or less square root of x many squares. But still, you can find a three-term arithmetic progression in squares, like this, 1, 25, and 49. But one can show that you cannot find a four-term arithmetic progression in squares. But what about cubes and other powers? So there's a famous result of Darmon and Merrill, and it states that whenever the power is at least 3, then you cannot find a three-term arithmetic progression in the end powers. So actually, what does it mean? This equation, x to the n plus y to the n, is equal to the 2 times z to the n. The only solutions are the trivial ones, means that x, y, z, they are all equal. And of course, this equation is reminiscent of Fermat's equation. Actually, it is hard as the Fermat's last theorem. Another nice example is the primes. The density of primes is 0 because, basically, one can immediately apply the prime number theorem because up to x, asymptotically, there are x over log x many primes. But there's a famous result of Green and Thaw, and it states that primes contain arbitrary long arithmetic progressions. So what is the relation between containing arithmetic progressions, arbitrary long arithmetic progressions, and density? You cannot decide immediately. So sometimes the density is 0, but still you can find arbitrary long arithmetic progressions. For example, here, for squares and cubes, the density is 0, but there are not arbitrary long arithmetic progressions in those sets. But it's a long-standing conjecture once. Now it's a theorem. Maybe it was conjectured by Erdos and Turan around 1935 that if your set is big enough, means that if your upper density is positive, then you can find arbitrary long arithmetic progressions in this set. For the length k equal to 3, this was resolved by Rhodes using a circle method from additive number theory, and Rhodes proved that if A is a subset of positive integers with positive upper density, then A always contains three-term arithmetic progressions. So whenever I say arithmetic progressions, maybe we should understand that it is non-trivial, because otherwise, as I said, any non-empty set contains trivial ones. So this is the first step, and it came from Rhodes. And the second one came from Semeridi, and Semeridi proved that the same thing, if A is big enough, if its upper density is positive, then you can find a four-term arithmetic progression in your set. But what about the other lengths? So then, after 6 years, in 1975, actually, Semeridi proved the long-standing conjecture of Erdos and Turan, and he proved that if A is a subset of positive integers with positive upper density, then A contains arbitrary long non-trivial arithmetic progressions. Of course, not an infinite one, but for every k, you can find a k-term arithmetic progression in your set. Okay? And this is a natural generalization of Semeridi's theorem, is a natural generalization of van der Waals theorem. Why? Because if you partition the positive integers into finitely many classes, okay, then at least one class should have positive upper density. Because if all of them would have 0 density, then does the set of all positive integers. So this is why Semeridi theorem immediately implies van der Waals theorem. Semeridi, used graph theory It's around 45 pages paper using many and difficult combinatorics, and it's difficult to follow. Then Fürstenberg reproved Semedri's theorem using ergodic theory, measure theory, and some dynamical systems. And also in 2001, recently, Gowers gave another proof using higher order Fourier analysis. So this is one of the cornerstones of uh, additive combinatorics. So it basically tells you that there are arithmetic progressions in your set, and you can also find a lower bound. But if you restrict your set up to n, it doesn't generally tell you that how many arithmetic progressions are there in your set. It doesn't give you the exact asymptotic. Of course, it's a difficult question, and it depends on the structures of your set have, right? So in this talk, our aim is to count exactly asymptotically. So we will have a main term and the error term, okay? And this time we are considering subsets of a finite field. So we are considering especially this set, the squares in a finite field. So we fix a prime P, then we consider the finite field Fp, and we consider its square elements. So unlike the case of integers, because in integers, squares have, right, zero density. But if you consider modulo P, everything changes. So here, right, the squares almost like one half, it consists almost of one half of the finite field. And we will count exactly how many k-term arithmetic progressions in this set. And our method will be based on some estimations of character sums. Okay, so this is our task today. And why this problem is important? Because, many people work on this problem, especially you fix k, so this is your length, and you take a big prime, p, bigger than k, then you are consider these consecutive numbers in FP, a plus 1, a plus k minus 1. So you have k many numbers, and you try to understand their patterns. So either they are quadratic residues or quadratic non-residues. So for this, you choose your signs. So epsilon 1, epsilon k. So they are from the set plus minus 1. And you count the number of elements in this set. So call it, for example, NP epsilon 1, epsilon k. So you count a's such that, for example, if epsilon 1 is 1, then for your first element is a, right? If epsilon 1 is a, then you first start with a quadratic residue element. Then you change your pattern. For example, if you always choose 1, so this is your Legendre symbol. If it is 1, if and only if you are a quadratic residue. For example, you can consider tuples of length k such that all of them are quadratic residues. So a is a quadratic residue, a plus 1 is a quadratic residue, and a plus k minus 1 is a quadratic residue. But actually, this is an arithmetic progression, right? So you have an arithmetic progression in squares, and your jump is here, it's 1. Okay. And for example, Aladov counted these quadratic residues when the length is 2 or 3. Then in the 1930s, Davenport handled this question. And actually, one can show that this is kind of well distributed, AQ distributed. Okay, and your expectation is the main term is P over 2 to the K. Because either you are a quadratic residue or you are not, right? And your density is, more or less P over 2. And if you consider two elements, your expectation is A and, for example, A plus 1. They are both quadratic residues is p over 4, for example. And so this is your main term, and this is your error term. You see in the error term, there is square root of p, and the coefficient of the square root of p is k minus 1. So main term is fixed, but maybe, I mean, you can make your error term smaller. So this is what we thought in order to study this problem. So here you are considering quadratic residues in arithmetic progressions, and your jump is always 1. So consecutive numbers, but this, I mean, may not be the case always. So you can consider arbitrary patterns. For example, you fix C1, Ck from the beginning. So K is fixed, P is fixed, and C1, Ck is fixed. Then you can also consider this set. So A in the finite field, non-zero, and the sign of A plus Ci is epsilon I. For example, again, if you choose all epsilons 1, this means that all of them should be quadratic residues. For example, if C1 is 1, Ck is k, then this time this is the previous problem. You are counting arithmetic progressions like A plus 1, okay? And you expect that all of them are quadratic residues. For example, then you can do this. C1 is 2, C2 is 4, right? Ck is 2k. Then you can consider A, or yeah, C1 is 0, C2 is 2. Okay, Ck is 2 times k minus 1. Then you are considering this time A plus 2, A plus 4. Then you want all of them to be quadratic residues. This means that you have an arithmetic progression with jumps 2, right? The common difference is 2 in squares. And again, actually, the main term is here p over 2 to the k. And again, the same methodology works, and your error term is around square root of p. And the constant term near square root of p is k minus 1. And there's also k over 2, but if you fix k, and since this is an asymptotic result, you allow p to grow, then of course, I mean, this is the main error term, right? Square root of p times k minus 1. So using this result, you can count how many k-term arithmetic progressions in squares, right? First, what you do, you take the jumps 1, then the common difference is 2, then the common difference is 3, then the common difference is 4, then eventually common difference is p minus 1. So this means that you have p many choices, right? Every time you are counting this set p times. So then if you multiply everything by p, more or less, this means that the number of KAPs in squares actually is given by the main term is p square over 2 to the k, and you get an error term. An error term, you multiply everything by more or less by p. So here you get k minus 1 times p to the 3/2. Okay, so this is what you get. Also, there is the second error term, but this is smaller compared to the p to the 3/2. Okay, so this is the result coming from the literature. So we try to estimate the error term in a better way. So this is our aim. And from now on, we will concentrate on this. But how to, I mean, do this? The famous result of Hasse, and it says that if you have an elliptic curve over a finite field, then actually the number of points on E is around p plus 1, and the error term you get is 2 times square root of p. So this means that this difference between minus 2 times square root of p and 2 times square root of p. Then Weyl worked on this problem, and he proved this result for finite fields, not just with p elements, but p to the m elements. And also here there is a, if you want to count the number of points on elliptic curves, you encounter with the Legendre symbol. So it's a multiplicative character. But also you can consider an additive character, and it's also done by Weil. And he proved that if you have a polynomial, nonlinear, and if it is not 0 modulo p, then you consider the Weil sum. So here is always EP is e to the 2 pi I x over p. And if you evaluate the additive character at polynomials, so here you have, right, p many sums, but actually there's a cancellation. So if your polynomial is good enough, mod p, it's not 0, then actually you see it's around square root of p. So there are many cancellations. And also, one can do the same result for the multiplicative characters. Weil also did it, and also extended Hassier's results to arbitrary finite fields. But here, one should use the Riemann hypothesis in finite fields. So this is the idea. The problem seems analytical, but actually one uses some, again, zeta functions, their behaviors, and it is related to algebraic geometry and analytic number theory. And this is a single variable sum. So what about more variable sums? And this is actually achieved by the work of Deligne, who extended Weil's theorem, but he also proved the Riemann hypothesis for finite fields. And this means, he solved the conjecture of Weil, the most difficult one, the Riemann hypothesis for finite fields. But of course, one cannot do this for all polynomials. Your polynomials at least should be smooth enough. So if your polynomial is smooth enough, this means if it is not factored too much, for example, then one can extend Weil's result. So this is the technology that we also used in our result. But what else? So we also need finite Fourier analysis. So if you have a function from the cyclic group Zn to C, its Fourier transform is another exponential sum. So this is actually reminiscent of the standard Fourier transform on reals, or 0, 1 or minus pi, it doesn't matter. So here we use the additive character. Then you can always recover your f from your Fourier transform, but this time you are not dividing by n. For the Fourier transform, you divide by n, but when you cover your function from the Fourier coefficients, and there is no n, but you can always express your function in terms of its Fourier transform. Here, everything is good because we are in a finite set, so there are no convergence problems, right? In general, it's not always true. Even you cannot express your Fourier transform. Your functions should be good enough, right? It shouldn't, grow very fast. Okay, this is the Fourier transform. Why it is important for this topic? Because you can count arithmetic progressions using the Fourier transform. How? So suppose that you have a subset A of Zn, and this is your K, the number of k-term arithmetic progressions, okay? Then actually the number of KAPs in this subset A is given by this n squared times the number of elements A power k divided by n to the k plus some error term. But error term is you see, it's a long sum, and there are many Fourier transforms. And one can think that this, can be hopeless because, I mean, first, the Fourier transform can be difficult. The second, I mean, there are many sums here. And maybe if you sum them up, the error term, I mean, may exceed the main term. So one should handle it, all the questions, I mean, the basic questions here. But for our set, squares are actually Fourier transform is good. Why? Because of the quadratic Gauss sum. So the quadratic Gauss sum is you have the additive character modulo p, and you evaluated the, so your polynomial here is a square polynomial, right? Like x square. And actually, Gauss spent more than 4 years to solve this problem because, I mean, it was very difficult problem at the time of Gauss, but actually maybe when he solved it, he gave many other different proofs for this because, I mean, one can show that this up in absolute value, the absolute value is always square root of p, but the sign changes up to modulo 4. If your prime is congruent to modulo 1 modulo 4, so it is square root of p. If it is congruent to 3 modulo 4, so it is I times square root of p. So is this the general pattern? Yes, but Gauss couldn't prove this for a long time, but eventually he managed to prove this. So this is a special case of the Weyl sum, right? Your polynomial is x squared. But in the case of Weyl, it is just a upper bound. It says that it is smaller than a constant time square root of p. But actually, you can exactly calculate it, right? So because of the quadratic Gauss sum, the Fourier transform of squares are not very difficult. And using the theorem of Gauss, the theorem of Gauss and the Fourier transform technique and the character sum estimates in several variables. So we prove the following theorem. Suppose that k is at least 4 and p is a prime number bigger than 3. Then if you want to count the k-term arithmetic progressions in squares, then it is given by two things, of course. The main term, of course, it cannot change. It is p squared over 2 to the k, but the error term this time, it is in absolute value smaller than k minus 2 over 4 and some small number, k minus 2 over 2 to the k minus 1 times p to the 3 half and some big O, right? So this is big O p. It doesn't matter, but at least if you use the literature previously, let me go back there. So you see it is the coefficient of p to the 3 half is k minus 1. So here, actually we improved it to, k minus 2 over 4. So this is actually, I mean, 4 times improvement. Because, I mean, if you count them single by single, as in the literature case, so you get k minus 1. But we counted them at the same time over a box, and this is why, I mean, we obtained maybe more cancellations. So here I stated the result for k at least 4, because when k is actually 3, you don't need the error term. If k is 3, then you can exactly count the 3-term arithmetic progressions in squares, and you see it changes up to modulo 8. 1, 3, 5, 1, 3, 5, 7, and it's always, I mean, computable. It's a rational polynomial in P. So, of course, I mean, the second question is, you find the main term and the error term. So is the error term necessary? I mean, can you make it smaller? Okay, for example, in the literature, it is k minus 1 time, times this number. Here we improve the constant, not the function, but maybe you can also improve the function. You can replace this function p to the 3/2 with a smaller function. Is it possible? To explain this, first, let me mention the big result of Bernoulli, Gretti, Harris, and Taylor. It's the Sato-Tate conjecture. So it was a conjecture conjectured around 1960s, but it's a theorem now. So after 50 years, it's a theorem now. It says that if you have an elliptic curve over Q without complex multiplication, it means that you don't have many symmetries. Then you consider this elliptic curve modulo P, and suppose that P doesn't divide the discriminant. So this time you get an elliptic curve, right, over FP. Then using the Hasse-Weil bound, you can always say that P plus 1 minus the number of points on this elliptic curve is always 2 times square root of P times the cosinus theta B. So this is a number depending on P, and it's called the Frobenius angle. And the Sato-Tate conjecture says that actually there is a equidistribution of this angle. This means that whenever you fix alpha and beta between 0 and pi, and if you consider the Frobenius angle lying between these two angles, okay, if you consider those primes and those thetas around this interval, and if you divide this number by the number of primes up to n, and the limit case, you obtain this limit. So this is a sine square distribution. So this means that actually there are many p's. This means that there are arbitrary large p's where your remainder can be very close to 2 times square root of p, right? So you cannot eliminate them. Okay, then using this, first we computed the number of 4 APs in squares. So this is your formula. So there are some rational polynomials in P and some Legendre symbols, but here you always 2, 3, and 6, but 6 is also 2 times 3. So if you know the Legendre symbol of 2, 3, I mean, which can be easily computed, right? Then actually you can compute this sum. But here, there is this elliptic curve, E, in the formula. And your elliptic curve is here. Y square equal to x times x plus 3 times x plus 4. Luckily, this curve, I mean, is a good curve. Like here, it doesn't have a complex multiplication. Also, its J invariant is non-integral. Okay, and using this, we can see that. So the number of non-trivial 4 APs in squares is given by, this is the main term, P square over 16. And the error term is here, is less than 1/8 times P to the 3/2 and some smaller error term. And this constant is best possible here. So you cannot improve your function P to the 3/2, but also you cannot improve this constant as well. So this error term is actually inevitable due to the Sato-Tate conjecture. Okay, so actually you need this error term. You cannot do much more. So this is the limit case for at least 4 terms APs. And okay, what about the 5 APs? Then there is another formula. We can also count 5 APs in squares. So it is basically rational polynomials in F and rational polynomials in those Legendre symbols again. And here, this time, we encounter with 3 elliptic curves. So there is E1, E2, and E3. All of them are good. This means that they don't have complex multiplication. But actually, in the literature, there is no mutual equidistribution result for the substitute conjecture. It is just for one elliptic curve. At least, I mean, I don't know, maybe there are recent results, but even there are no mutual, I mean, equidistribution for two curves. So maybe one of them brings, I mean, too much error term, but the other one may cancel it. So as a result, you may expect that you can, I mean, get rid of the term p to the 3/2. So maybe this is not that case, but actually one can also do this. The number of 5 APs in squares is again given by the expected error term, p square over 32. This is 2 to the 5. And actually this term again, the error term, p to the 3/2, it is also inevitable. I mean, it is best possible. So you cannot apply the substitute conjecture immediately, but actually at some point you can do some other stuff. Eventually those curves are related in a sense, but then you manage to prove that this error term is inevitable. So generally you show that this is the, so what we proved that we've improved the error term for every k. We counted the three-term arithmetic progressions for 3. There is an exact formula. For the length equal to 4, so we counted them exactly, and we proved that the error term and the constant is unavoidable. And for 5, we actually did the same thing. We counted them exactly. One can find all polynomials here, and there are 3 elliptic curves, and one can show that again the error term is inevitable. I mean, you cannot replace this function with a smaller function. So this is also kind of a Riemann hypothesis case. So there is one term, and you can cancel at most square root. Yeah. So actually, I am done. I think. Yeah. We are in time, right?
Yeah, thank you, Haydar.
Question.